All right. So, in my last lecture, I started with power electronic, and I want to complete this session and then start the power systems. Okay. In this slide, I want to talk about PWM converters. So, pulse width modulation or PWM converters use high frequency switching to transform a constant DC voltage into a variable amplitude AC output. This is achieved by precisely controlling the duty cycle, the ratio of the on time of the switch to the total switching period, as I told you before. And by varying this duty cycle in a sinusoidal pattern, the average voltage across the load can be shaped to resemble sine wave, So the use of PWM allows for efficient and precise control over the output voltage and frequency, which is a key requirement for modern inverters. Single-phase PWM converters typically use an H-bridge circuit, which consists of four switches. The two primary methods of controlling these switches are unipolar and bipolar PWM. Bipolar PWM is the simpler of the two. It switches the two legs of the H-bridge in complementary fashion. So the output voltage of the converter alternates between a positive and negative DC voltage with the duration of this pulse controlled by high frequency carrier signal. So while straightforward, this method produces an output voltage with a higher harmonic content and more switching losses, making it suitable for less demanding low cost applications. So in contrast, unipolar PWM is a more sophisticated technique. It also uses a four switch H bridge, but it generates an output voltage with three levels: positive, negative, and zero. So this is achieved by switching only one leg of the bridge at a high frequency, while the other leg remains at a constant voltage for a half cycle. This technique results in a smoother output voltage waveform, significantly reducing the harmonic content and minimizing switching losses. Due to its superior performance, unipolar PWM is the preferred method for medium power applications that require higher quality output, such as in residential solar inverters, for example. Okay, this slide, sine wave three-phase PWM converters describes the operation, applications, and harmonic characteristics of three-phase inverters that use pulse width modulation. A three-phase PWM converter is a crucial component in modern power electronics, acting as a bridge between a DC source and a three-phase AC load. The circuit typically consists of a three-leg bridge with each leg containing two switches. The primary objective is to generate a balanced set of the three-phase AC voltages that closely approximate sine waves. So this is achieved by independently controlling the switches in each leg using a PWM technique. So the the firing pulses for each leg are shifted by 100 degree to create the required three-phase output. The main advantage of this topology is to its ability to provide highly efficient and precise control. The output voltage can be varied by changing the modulation index, and the frequency can be adjusted by changing the frequency of the carrier signal. So a key consideration for these converters is their harmonic content, while the high frequency switching helps to reduce low order harmonics. The output voltage waveform still contains high frequency harmonic components. So these harmonics can lead to losses in the load and the converter itself. So despite this, the overall total harmonic distortion is much lower than in older, less sophisticated square wave inverters. So the application of three-phase PWM converters are widespread and critical to modern electrical systems. They are the core of the AC motor drives, providing the variable voltage and frequency needed for efficient speed and torque control. They are also essential in grid-tied inverters, which are used to connect renewable energy sources like solar and wind power to the utility grid. So these converters ensure that the variable power from the source is transferred into the stable grid compliance AC signal. So in this slide, I want to talk about the space vector modulation, which is an advanced and highly efficient PWM technique used primarily for three-phase converters. Unlike traditional sinusoidal PWM, which controls each of the three phases independently, SVM treats the entire three-phase system as a single rotating voltage vector, and the algorithm works by calculating the desired output voltage vector at any given moment and then synthesizing it using a combination of the eight available switching states of the converter's three legs. So these eight states correspond to eight fixed voltage vectors in complex plane. By carefully selecting which vectors to use and for how long to apply them within a switching period, SVM can accurately reproduce the desired rotating voltage vector. So compared to conventional sinusoidal PWM, SVM offers several significant advantages. First, it achieves a higher DC bias voltage utilization, meaning it can produce a higher output AC voltage for the same DC input voltage, often up to 50% of more. So second, it generates a cleaner output waveform with a lower harmonic content, which leads to reduced switching losses in the converter and smoother, quieter operation of the load, such as an AC motor. So this improved power quality and efficiency make SVM the preferred modulation strategy for high performance applications where precise control and energy efficiency and paramount, including electric vehicles, industrial motor drives, and grid-connected renewable energy systems can be applied. So this slide also provides a high-level introduction to the purpose and types of motor drives, also known as variable frequency drives or VFD, or adjustable speed drive or ASD. At their core, motor drives are sophisticated power electronic devices designed to control the speed and torque of the electric motors. They achieve this by converting a fixed voltage, fixed frequency AC or DC power source into a variable voltage, variable frequency supply for the motor. So this contrasts with direct online start, which simply connects the motor to the grid at its full rated voltage and frequency. The primary motivation for using a motor drive is the significant benefit it provides in terms of energy savings and process control. Many industrial applications such as pumps and fans have a variable load. VFD allows the motor to operate at a reduced speed during a low load period, which drastically cuts down on energy consumption. Furthermore, in process that require precise speed and torque, such as in manufacturing or on a conveyor belt, drive periods the necessary control to optimize the operation. Another key advantage is improved reliability. A stop-start function, a standard feature of most drives, gradually ramps up the motor speed which reduces the mechanical stress on both the motor and the connected machinery, thus extending its lifespan. So this slide also distinguishes between the two main types of motor drives based on the input power, single phase and three phase drives. Single phase drives are simpler and are used for low power applications such as in household appliances or some small workshops. So they are less efficient and offer more basic control. In contrast, three-phase drives are the industry standard for high power industrial applications. They are highly efficient, offer superior control capabilities, and are a key component in a wide range of industrial processes. So this slide focuses on the fundamental methods used by motor drives to control the speed and torque of AC motors. The core principle for controlling an AC motor's speed is directly tied to the frequency of the power supply. This relationship is defined by the formula NAS is equal to 120 times F over P, where ns the synchronous speed of the motor in revolution per minute, f is the supply frequency in hertz, and p is the number of motor poles. So by varying the output frequency of the motor drive, the rotational speed of the motor can be precisely adjusted. So to effectively control both speed and torque, different methods are employed. The most common and simple method is V over F control, also known as scalar control. This technique maintains a constant ratio of voltage to frequency, which keeps the magnetic flux in the motor constant and prevents it from reaching saturation. So this method is suitable for basic applications like fans and pumps where high dynamic performance isn't a requirement. However, for more demanding applications, a more advanced technique called vector control or field-oriented control can be used. So this method treats the AC motor like a separately excited DC motor by independently controlling the motor's flux and torque producing current components. This allows for much more precise and dynamic control of the motor speed and torque, especially at low speeds. So an even more advanced method is direct torque control, which directly controls the motor's flux and torque without relying on a complex mathematical model, offering an extremely fast torque response. Okay, the majority of VFD applications involve operating the motor at speeds lower than its maximum rated speed. So this is particularly beneficial for loads with variable torque characteristics such as fans and pumps. For these applications, the power required decreases with the cube of the speed, meaning that even a small reduction in speed can lead to significant energy savings. So by using a VFD to match the motor speed to the exact process requirements, plant operators can drastically reduce their energy consumption. So VFDs are also crucial for applications with high inertia or high starting load like conveyors and crushers. Instead of starting abruptly at a full voltage and frequency, a VFD can perform a soft start, gradually ramping up the motor speed. So this reduces the immense mechanical and electrical stress that would otherwise occur, extending the life of the motor and the mechanical system. So operation um, above rated speed or field weakening. Regarding this topic, it is also possible to operate a three-phase motor above its rated speed, although this is more specialized applications. So this is achieved by a technique called field wicking. So while operating at or below the rated speed, the VFD maintains a constant voltage to frequency ratio to ensure the motor's magnetic flux remains constant. However, to operate above the rated speed, the frequency is increased while the voltage is held constant at the maximum available value. So this process weakens the motor's magnetic field, which allows the motor to spin faster. The key trade-off here is that as the speed increases, the torque producing capability of the motor decreases. So this technique is commonly used in electric traction systems, such as in electric vehicles and trains, where high speeds are sometimes needed for short periods and reduced torque is acceptable. So this slide introduces AC to AC converters, which are power electronic devices used to directly convert a fixed AC voltage into a variable AC voltage without alternating the frequency. So these are often referred to as AC voltage controllers. So the primary function is achieved through phase angle control, a method similar to what's used in control rectifiers. The converters use semiconductor switches, most commonly thyristors or triacs, which are turned on at a specific point in each half cycle of the input AC sine wave. This point is determined by the firing angle alpha. By delaying the turn on of the switch, a portion of the sine wave is chopped, which reduces the overall root mean square or RMS voltage value delivered to the load. So the more the firing angle is delayed, the lower the output voltage can be reduced. So these converters have numerous practical applications where variable voltage is required. A very common example is in lighting control, such as with household dimmer switches, where a triac is used to smoothly adjust the brightness of a light by varying the voltage. So they are also used for heater control in industrial settings to provide precise temperature regulation for processes like electric furnaces and ovens. For low to medium power motors, AC voltage controllers can be used for motor speed control by changing the voltage supplied to the motor, making them suitable for applications like fans and pumps. So this slide explains how AC to the AC converters are used as a motor soft starters. This application addresses a significant problem with traditional motor starting methods. When an AC induction motor is connected directly to the power grid, direct online, or we call DOL start. So this motor draws a very large inrush current, typically 6 to 8 times its normal full load current. So this high current can cause a momentary drop in the voltage of the electrical system voltage stack, affecting other connected equipment. So furthermore, the sudden application of the full voltage and torque creates immense mechanical stress on the motor shaft, gears, belts, and other mechanical components, leading to uh, premature wear and tear. So a soft starter is an electronic device that uses a thyristor or triacs to eliminate this problem. So instead of applying full voltage immediately, the soft starter gradually increases the voltage to the motor. It does this by controlling the firing angle of the thyristors, starting with a large angle to apply a low voltage and then slowly decreasing the angle over a set period. So this voltage ramping allows the motor to accelerate smoothly and gradually. And the benefit of the using a soft starter are substantial. I listed some of them here in this slide. First, it limits the starting current, preventing harmful voltage sags on the power system. Second, it reduces mechanical stress, providing a smooth, jerk-free start that protects the motor and mechanical components, thereby extending their lifespan and improving overall system reliability. So this makes soft starters an excellent choice for a wide range of industrial applications such as pumps, fans, and compressors. So this slide explains the crucial role of reactive power or VAR compensation and introduces two key devices used for this purpose: static VAR compensators or SVC and dynamic VAR compensator or DVR. So reactive power is the fundamental part of AC power system. Just to refresh your mind, necessary to create the magnetic fields required by inductive load like motors and transformers. However, a high demand for reactive power can lead to a low power factor and poor voltage regulation, negatively impacting the efficiency and stability of the grid. Power electronics provide highly effective solutions to this problem by enabling the rapid and precise injection or absorption of reactive power. A static VAR compensator or SVC is a shunt device connected in parallel with the power line. It uses a thyristor control reactors and or thyristor switch capacitor banks to dynamically adjust the amount of reactive power drawn from or supplied to the system. By doing so, the SVC can quickly respond to changes in the load, maintaining a stable voltage profile and improving the power factor. So this makes it an essential tool for improving grid stability, especially in industrial facilities with large fluctuating loads like arc furnaces or ruling mills. So in contrast, a dynamic voltage restores or DVR is a series device. It uses an inverter to inject voltage in series with a power line to compensate for voltage disturbances. So when the main voltage supply experiences a voltage sag or a temporary drop or a soil, a temporary rise the voltage, the DVR rapidly injects compensating voltages to restore the voltage at the load terminals to the desired level. So this protects critical and sensitive equipment such as that found in semiconductor manufacture plants from the harmful effects of grid disturbances. Both SVC and DVR are vital for modern power quality management, ensuring the grid remains reliable and resilient. Okay, this slide also explains the crucial role of reactive power for compensation and introduces two key devices used for these purposes, SVC and DVR. Reactive power, so as I told you, is necessary to create the magnetic field required by inductive loads. So um, I, I already talked about SVC and DVR. So in the previous slide, this one just showing more applications. Okay, this slide introduces flexible AC transmission systems or FACS devices, which are power electronic devices designed to enhance the control, stability, and power transfer capability of AC power grids. They are a modern solution to long-standing power system challenges, providing a dynamic and rapid response that traditional mechanical controllers cannot. So the main function of FACS devices revolve around improving the performance of the transition network. First, they can increase power transfer capability by controlling parameters like voltage, impedance, and phase angle. They can route more power over existing transmission lines, effectively increasing the line's capacity without the need for building new infrastructure. This is particularly valuable in long distance power corridors. Second, they are crucial for enhancing grid stability. They can quickly dampen power oscillations that can occur after a fault or disturbance, helping to prevent widespread blackouts. Finally, fax devices play a key role in improving power quality. They can regulate bus voltages and provide dynamic reactive power support, which helps maintain a stable and reliable power supply for customers. Okay, this slide categorizes fax devices based on how they are connected to the power system and explains their specific applications. The two primary category are series and shunt devices, with a third category combining both. So series fax devices are connected in series with the transmission line. Their main function is to control the effective impedance of the line, which directly influences the amount of power that can be transferred. They can inject a voltage that is in quadrature 90 degree with a line current, effectively increasing or decreasing the apparent impedance and thereby controlling the power flow. The static synchronous series compensator, or SSSC, also is a key example. It uses a voltage source converter to inject a variable voltage, making it highly effective for power flow control and enhancing a transmission line's transfer capability, particularly in long distance corridors. So shunt fact devices are connected in parallel or shunt with the transmission line. Their primary role is to control the bus voltage by dynamically injecting or observing reactive power. The two most common examples are the static var compensator, or SVC, and the static synchronous compensator, or STATCOM. So an SVC uses thyristor to switch capacitor and inductor banks, while a STATCOM uses a voltage source converter. STATCOMs are generally preferred over SVC for their faster response time and superior performance in maintaining voltage stability. So both devices are essential for voltage support and improving power quality in industrial or urban areas with high reactive power loads. Finally, some advanced devices combine both series and shunt functions. The most notable example is the UPFC, or Unifying Power Flow Controller. As the most versatile and complex fax devices, it can simultaneously and independently control three key power system parameters: line impedance, bus voltage, and phase angle. This comprehensive control allows the UPFC to solve a wide range of power system problems, from congestion and stability issues to local voltage regulations. Okay, I don't know. Sorry, are you online, right? Okay, I think just I lost PowerPoint. Okay, this slide, correcting power system problems. It's talking about correcting the power system problems, devolves into the practical application of fax devices by focusing on how to select the right device to solve specific power system issues. So the key is to first assess whether the problem is local or global in nature, as this dictates the appropriate solution. So a local problem is an issue confined to a specific point or a small area of the power grid, such as a drop in voltage at a substation that supplies a large industrial load. In such cases, the most suitable solution is a shunt fax device like a static synchronous compensator, a STATCOM, or a static VAR compensator, SPC. These devices are designed to inject or observe reactive power at a specific bus to maintain stable voltage profile. For instance, a STATCOM can quickly inject reactive power to support the voltage when a large motor starts, preventing a voltage sag that would otherwise affect other nearby equipment. A global problem, on the other hand, affects a large portion of the power system. Examples include transient stability issues, power oscillations between different regions, or congestion on long transmission lines. For these issues, a different approach is required. A series fax device such as static synchronous series compensator, or SSC, is either for increasing the power transfer capability of a congested line. So by controlling this, the effective impedance of the line, it can push more power through an existing corridor. For the most complex global problems that require simultaneous control of multiple parameters, voltage, impedance, and phase angle, the UPFC is the ultimate solution. So while it is the most expensive and complex, its versatility allows it to address a wide range of interconnected stability and power flow issues. This slide provides an introduction of HVDC transmission, high voltage direct control current, a modern and highly efficient method of transmitting large amounts of electrical power over long distance. So as at its core, HVDC transmission system relies heavily on power electronic converters. The reason for this is that AC power from the grid cannot be directly converted to HVDC without a crucial conversion step. At the sending end of the transmission line, a rectifier, which is essentially a power electronic AC to DC converter, takes the high voltage AC from the generating station and transforms it into high voltage DC. So this DC power is then transmitted over the long distance line. At the receiving end, an inverter, which is DC to AC converter, performs the opposite function, converting the HVDC power back into AC to be used by the local grid. So these converters, typically built with high power semiconductor devices like thyristor or IGBTs, are the enabling technology that makes HVDC transmission possible and allows for precise control of the power flow. So we have high voltage AC transmission as well. So high voltage HVAC is the traditional method used for over a century, so relying on transformers to step up voltage for transmission and step it down for distribution. So while it's a well-established technology with a robust infrastructure, it has significant drawbacks for long distance. A major issue is high transmission losses due to reactive power from the inductance and capacitance and the skin effect, which causes current to travel on the other surface of conductors, reducing the effective area. So HVAC systems are also susceptible to stability problems such as transient instability, and power oscillations over long lines. HVDC transmission is a modern power electronics based method where AC power is converted to DC for transmission and then converted back to AC at the destination. So it offers significant advantages for long distance, typically over 500 kilometer, and submarine cables. So lower key advantage of HVDC over HVAC has been summarized in this slide. So first of all, lower transmission losses. So because DC lines have no reactive power and no skin effect, they experience much lower power losses. So this makes HVDC for more efficient for transmitting power over very long distances. So another advantage is fewer conductors. A bipolar HVDC line requires only two conductors, one positive and one negative, compared to the three conductors needed for three-phase HVAC lines. So this reduces the cost of the line and the size of the towers. Another benefit is no stability issues. So HVDC systems are not subject to the stability limits and synchronization problems of HVAC. This allows them to easily connect to synchronous AC grids, even if they have different frequencies. Another benefit is cost effectiveness. While HVDC converter stations are expensive, the lower cost of the transmission line itself and reduced power losses make HVDC more economical for the long distances. And For long distance underground and undersea cables, HVDC is often the only practical solution. AC cables would suffer from severe losses due to the cable's capacitance, making them inefficient or unstable. So this slide titled "Practical Application of HVDC" outlines the key real-world uses of HVDC. HVDC is the preferred technology for specific scenarios where conventional AC transmission is either inefficient, technically challenging, or not feasible. The primary application of HVDC is for transmitting a large amount of power over long distance. HVDC is also valuable for connecting synchronous AC grids, grids that are not synchronized. It means that their frequency or phase angles are not locked, cannot be connected directly with an AC line. So an HVDC system, however, can act as a back-to-back link, converting the AC from the one grid to DC and then back to the AC for the other, regardless of the synchronization state. So this is crucial for international grid interconnections and for systems like Japan's, which have both 50 Hz and 60 Hz grids. Furthermore, HVDC is the only practical solution for long distance undersea and underground cables. With AC cables, the cable's inherent capacitance creates a large charging current that would lead to significant power losses and make long distance transmission impossible. So since DC has no frequency, this problem is eliminated, enabling the transmission of power to islands or across continents via subsea cables. Thank you so much for your attention. I wanna have a break, 5 minutes, and then start the second part of my presentation. Do you have any question? Hello, are you here?